Hey everybody, you're listening to the BTW Media Podcast, the show that explores the stories, innovations, and insights for people who love technology and the internet.
Hi everyone, welcome back to Blue Tech Wave Media. Today I'm delighted to speak with Dr. Nitinder Mohan, a faculty member in the Department of Electrical Engineering, Mathematics and Computer Science at the Delft University of Technology in the Netherlands. He leads the SPEAR Lab, which is short for Systems and Protocols for Edge-Enabled Internet. Dr. Mohan's work consistently pushes the boundaries of how we think about the performance, adaptability, and the real-world deployment of modern networks. So how are you, Dr. Mohan?
Hi, good morning. I'm really good. Glad to be here.
So I prepared several questions for you. The first one is, as I mentioned, you lead the SPEAR Lab. Could you briefly introduce its core focus areas, particularly in edge computing? What would you say is the biggest challenge right now?
Awesome. Yeah, so I'm the lead of the Systems and Protocol for Edge-Enabled Internet lab. So this lab is fairly new, but the research that I've been doing has been going on for the last couple of years now since I did finish my PhD. So the SPEAR lab, I feel, it falls within the intersections of edge computing systems and also internet measurement. So what we intend to do is tackle real issues of how cloud computing systems right now and the traditional internet technologies are kind of merging with each other. But if you look into the operators, they are still fairly two distinct clouds that are working on it. In the last few years, what we have seen is that compute servers are no longer confined to these offshore data centers. Now they're moving much closer to the users, even becoming part of your ISP networks, right? And similarly, your internet is no longer just a way to connect to these third-party servers which are far off, but essentially they act as middleboxes in the middle where you can actually do compute over them. If you think about new technologies, now there's talk about 5G. There was a lot of promises behind 5G on what this kind of technologies would enable. From a modern internet protocols perspective, what people intend to do is enable these extremely latency critical applications like cloud gaming, augmented reality, virtual reality. So these applications, they no longer require that you talk to this one large data center far off, but essentially they require computations much, much closer to you, maybe computations while the data is still going towards the end server, right? And to enable that with the existing technologies, there's a huge dichotomy between what we have so far and what the intention is. And this is where SPEAR Labs comes in. So essentially what we intend to do is we build real systems. And for building real systems that enable edge computing, mostly focusing on orchestration aspects, we also look into what is the end-to-end performance from an internet-wide scale is. So on one end, we do a lot of internet measurements. We look into a lot of transport protocols performance. We look into ISP performances. We look into application performances. And then we gain from the insights from those measurements. And we use that to make our systems that we design more optimized to operate over these networks, which are no longer as distinctly enabled as you would consider a regular operator network would be. So it's essentially a cyclic network, where we do build systems, we do measurements, and then we build systems again to improve on those systems. Yeah, exactly.
Also, as you mentioned that traditional protocols like TCP are struggling in modern environments. In the context of LEO satellite networks, what would you say are the most critical performance gaps now?
It's a really good question. So essentially, before I jump deeper into the TCP aspect, let me just build a foundation on these LEO satellite internet providers. So this seems to be a new trend where LEO operators, they are deploying a lot of satellites. And the traditional sentiment when somebody talks about a LEO satellite operator is that, okay, these are satellite providers, right? So you go into the space and that's why you have a better connectivity because you no longer have to get a local base station that you have to connect to. So you're no longer dependent upon government fundings and something. Your satellites are deployed. They're revolving around the earth. They will always come back. If you have dense enough connectivity, you will be able to get internet. But what we see when we do measurements on these networks and we look deeper into how these networks operate, we realize that they are not really space networks. They are still ground networks because your satellites is only analogous to your base station. So instead of you connecting to a cellular base station, you connect to satellite. But then the satellite will put your connection back on the ground. And they do this via ground station. Then your connections from ground stations go towards your point of presence. And essentially, if you do not have enough ground stations and point of presence as a satellite network operator, you will have a really bad performance. And we saw this when Starlink was also becoming expanded its infrastructure, even though Starlink was deploying a lot of satellites in the space, they were still not able to provide really good connectivity for regions like Asia and Africa because they did not have enough ground infrastructure in those places, right? And then they have to actually put in a lot more investments on getting licenses in those regions, deploying ground stations, figuring out peering and all of these other situations to actually reduce that latencies a lot. And as we start to see lot more of these LEO satellite operators emerging now, OneWeb is coming up as well. Kuipers is also planning to put up a lot more satellites as well. You will start to see these different dynamics emerge, right? So your terrestrial networks, they will going to focus on your mobile connectivity, and satellite operators will be considered as, okay, more resilient way or maybe more accessible way to get your connectivity. But behind the scenes, they both are using the same backhaul and our regular internet infrastructure, right? So the way they operate is going to be a little bit different though, because your links are different, your connectivities options are different, latencies are different, throughputs are different. So we will see a lot more different ways on how transport protocols and applications behave on LEO satellite operators versus regular terrestrial operator networks, right? So we did a few measurements of our own. If you look into Starlink performances, for example, today, you will see from a latency perspective, they are doing pretty well, right? So they give you almost 30 to 40 millisecond latencies if you are in US or Europe. In Africa, now they're trying to reduce their latencies by a significant margin by putting more ground infrastructure, but still the latencies have a significantly high variability. And that's because satellites, they are doing a lot of handovers, you do not have enough capacity at the ground station, and so on. If you try to put your existing transport protocols and your existing routing protocols, you will see that the performances are not going to work very well on these LEO operators, right? So you need to have some way of how you can integrate your existing terrestrial networks with your non-terrestrial networks, so you can actually have a more complete ecosystem on how you can get them to interact and work with each other.
Is the cost of the satellite infrastructure more expensive?
Your starting cost is definitely more expensive. One can then do some economics, mathematics, back of the hand calculations to see over, say, 5-6 year period, how is it going to evolve. So satellite costs are one-time cost to put satellite in the space. A regular lifetime of these satellites are close to 5 to 6 years. Now we see that the lifetime is around 3 to 4 years for Starlink. So that's the major investment point. For terrestrial networks, however, the major investment point is, number one, getting licenses. Number two, putting base stations in different regions, right? Especially if those are terrains which are not easily accessible, then you still need to go and deploy your base station technologies there. Number two is then doing maintenance on those base stations. So for satellites, there is no maintenance because you cannot access those, right? So as they die after 5 years, they die after 5 years, and they need to deploy more. So the startup cost might be high, but maybe the runtime cost over a period of time, they might be lower. In terms of accessibilities, you can also say because satellites, if you deploy them over US, they will be available on Australia as well. So you deploy this cost once, and then you have a complete global connectivity. But for terrestrial networks, if you deploy a cellular base station in a particular region, you only cover that particular region. You are not able to provide connectivity to inaccessible regions, right? And this is one of the advantages.
So from your research, what are some early findings or promising directions on integrating LEO satellite networks with existing internet operations?
Yeah, so this is a good question. So as of now, there seems to be a difference of opinions on how LEO satellite operators also want to pitch that their network is doing well. So usually what they will do is provide you latency to point of presence as your key mark metric for understanding if they have good coverage in an area or not. So if you go to, for example, Starlink website, they will show you with a very pretty map that, oh, in this country, we are giving you 30 milliseconds or so, and we have enough capacity. But essentially behind the scenes, what's happening is point of presence is only to get access to the internet. You still have to go to wherever your endpoint server is, which comes back to what Spear is also trying to work on, is how do you get end-to-end application performances as best as possible. You brought up CDNs, right? So I'll give CDNs as an example. Let's assume that, for example, Africa, if a new LEO operator comes in, it doesn't have enough investment to deploy ground infrastructure there, right? Which essentially means that if you are connecting from Africa, you can use the inter-satellite links to get to wherever the nearest ground infrastructure is, which for you is going to be Europe, right? So for you, if you go to European point of presence, you can say, okay, my latencies are on the order of 100 milliseconds and everything is fine. But in reality, you might be fetching a web page which is really relevant to your African subcontinent, right? So in Nigeria, I'm looking at content which is relevant to Nigeria. If I exit out of Frankfurt, I'm not going to get that content in Frankfurt, which essentially means I come back using terrestrial connectivity, which is anyways bad, and then go back to Nigeria. Then I get that content. I go back to Frankfurt, and then I use the satellite links to go back. So essentially, I'm getting the worst of both worlds if I'm trying to get the right connectivity from that region. And this is just one example. We also see examples where how do you do, for example, compute service connectivity from satellite links, right? Our existing internet was designed from the perspectives that everything is connected on the ground. You have very hierarchical zones, and you can figure out which user is close to which particular service using DNS, GeoIP feeds based on this kind of a terrestrial hierarchy. But LEO satellite networks kind of completely depart from this trend, right? You have no idea if behind the scenes the user is coming from the same region if it's using one particular point of presence, or it might be coming from a different region altogether. And this calls for ways on how can you bring more closer integration? How can you actually expose the services that are accessible on your terrestrial networks to these non-terrestrial network operators, so you can have a better mappings of CDNs and compute services and so on.
Flexible ecosystem that covers all.
Exactly.
Thank you very much. So the last question is, you also work on large-scale internet measurements. Have your results ever contradicted common assumptions about how the internet or its protocols behave in practice?
This is a very interesting question as well. So personally, from my research objectives as well, or from internet measurements, my thought process always has been that you want to break the assumptions that exist in large-scale populace, right? People might think that, okay, this protocol or this particular technology should behave this one way. What we usually find by measurements is that it does not. So I'll give you two really good examples that we had. So one was coming from a systems perspective. And this was when we were just starting out our research on understanding how do you build edge computing systems. There was a lot of money being thrown around on the term edge computing. Everybody was like, okay, we can do a lot of stuff on edge. And why do you want to use edge? Because edge is going to miraculously bring down your latencies and it's going to enable these applications, right? So what we essentially did was we ended up doing a large scale measurements to cloud operator networks, right? Most of the cloud operators, we looked into 7 major cloud operators globally. We mapped from all users around the globe using cellular connectivities, Wi-Fi connectivities, your fiber connectivities to the nearest data centers. And we tried to understand what kind of latencies are you getting. And if you were to put those compute servers closer to the users now, what kind of latency gains are we talking about? And this was one paper that got accepted in Hotnets 2020, where we essentially highlighted that edge computing is not going to bring down your latencies. If latency is your objective on how you want it, why you want to do edge computing, because what we see is that the latency benefits are significantly lower and most of the latencies are concentrated at the last mile, your cellular link or the Wi-Fi link, right? Once you're already at the backhaul, your latencies are fairly short to your data centers. And data centers also peer directly with most of your large ISPs in Europe and US. So there is not enough piece of the pie from a latency perspective. So the main reason why you should be doing edge computing is on either improving the performance of your applications. How do you build an ecosystem on how can you do this compute? Not really for chasing latency gains, right? And this was initially met with a very critical thought, but at that, after a few years, people have understood this now as well. And now you see edge computing solutions which are more catered towards building these ecosystem and not really from a latency perspective. So this was one good example why internet measurement gave us more insights. The other one was we were very interested in understanding multipath TCP performances. So if the listeners are not clear, Multipath TCP is an extension to a TCP protocol, which allows you to use multiple paths simultaneously, as the name suggests. So how the protocol works is it has a header on top of a TCP extension, which signifies that now this protocol is using multipath. And then it also signifies which particular paths are you using end to end. So you might have an access to Wi-Fi and access to cellular. So instead of using one over the other for each TCP stream, what you can do is you can establish both connections simultaneously and run them as a multipath ad hoc end to end, right? So you can essentially double your bandwidth. And there's a lot of work that went into this from a practical adoption perspective, In 2020, the protocol was actually standardized by IETF as well. So after 6-7 years of significant operations. So we started doing a lot of measurements and understanding who is actually using multipath. Does it actually work in practice? So we did a lot of scanning studies as well. And what we realized is that multipath TCP is really not liked by internet middle boxes because they do not recognize these TCP extensions that exist on multipath. So they block most of the multipath connections, or they would send you bad syntax to the sender, emulating that you are talking to an MPTCP server, but essentially you're not really. So there can be security loopholes there as well. So even after like 7 years of efforts in standardizing, a few years of multipath research efforts, what we saw was that only a handful of parties were actually using multipath TCP in real internet. Most of this was because of Apple. And very recently, even Apple died down and it's not using multipath TCP anymore. We actually open sourced all our studies. So if you go to mptcp.io, you can see from the last 5 years how multipath adoption has changed both for V0 and V1 and how many ASs on the network are actually using multipath and so on. So this was another one that even if a protocol gets standardized, it doesn't mean that people will end up using that protocol. So, and if somebody wants to use it, there might be some unwanted problems with the internet ecosystem that might not allow you to use it because not everybody is compatible with that protocol.
So thank you very much, Dr. Mohan, for sharing your insights and the exciting work taking place at the Sphere Lab and your research. It's been a fascinating conversation on the future of networks. We touched upon the challenges of edge computing and the potential of integrating LEO satellites into the internet. I'm sure our audience will walk away with a deeper understanding of both the technical and practical dimensions of your research. We truly appreciate your time and look forward to the progress of your work. Thank you very much, Dr. Mohan.
Thank you. It was a pleasure.
Thanks for joining us for another episode.